Okay, so these are the kind of the applications of exponential and logarithmic models. So what we have here is an exponential model for the growth of bacteria. And this happens when you have some kind of organism, a microscopic organism, bacteria, viruses, where there's an unlimited supply of food and resources. So it keeps growing and growing and growing. At some point, there's going to be competition for resources. In that case, we might have a logistics growth model, but in the initial phase, it can behave in a exponential fashion. What we have to do here is we have to figure out what this K constant is. So the 100 is what we would call the initial amount. So there are 100 bacteria to start with. And that's because if you put t equals 0 in for the exponent here, k times t equals 0, you'll have k times 0, which is 0, and e to the 0 is 1, so you just end up with 100. So they don't ask us anything, but what we can say is that t equals 0, or at t equals 0, n equals 100. And so what they've done is they've given you the count at some other time, 5 hours. Since they didn't specify here what the time unit was, they did say hours here. So what we're going to do is we're going to find k based on this information. And then once we have k, we can just plug in, well, we can use that to figure out how much time it takes to double the population. So to do this one, basically we have n of t. So this n is a function of t, and the function is what's written. And what it says is when t equals 5, n equals 300. So all you do is for n you put in 500. And for t, you put in 3. So I'm just going to change the order there. So it's 100 to the 3 times k. So we have to solve for k. So we're going to use the properties of logarithms, or what we can do is we can take the log of any base, but we only have the natural log and the log base 10 in our calculators, so that's what we'll use. We'll use the natural log. So what we do is we take the natural log of 500, and that's equal to the natural log of 100 to the 3k, 3 times k. So the properties of logarithms say that you can bring that exponent, which is 3k, outside. So we have 3 times k times the natural log of 100. If we divide both sides by the natural log of 100, we'll get 3k. And then we divide both sides by 3, so we'll have the natural log of 500 divided by 3 times the natural log of 100. And now we can plug that into our calculator. So the natural log of 500 is 6.21. We divide by 3, which is 2.07. And we divide it by the natural log of 100. And the answer I get is 0.4498. So I'm going to round it off to 449. So now we can go back and further define the function as 100e to the 0.449t. And just to double check that we did it correctly, if we plug in, so if we do n of 3 again, that's at 3 hours, you get 100 times e to the 0.449 times 3. So let's do that. So we take 100 times e to the 0.449 times 3, and that comes out to be not the right answer. Okay. So the question is, what did I do wrong? So you can see how, you want to check your answers. Maybe I just plug the wrong numbers in my calculator. Let me just double check here. Natural log of 500 is 6.2. And yeah, see what I did differently than I normally would do, but I'm not sure why it's not working out right. Well, let's show you where I... No, well, that's not right. That's true. Okay, I just realized I did something wrong, so I'll come back. It's because I wrote this down. Forgot the e part here. Okay, so you get 100 times e to the 3k. So what we're going to do is we're going to divide both sides by 100. So this will become 5. So you get 5 is equal to e to the 3k. So to make this work out, we're going to take the natural log of both sides. And what that does is it allows us to use the properties of exponents. So the left-hand side still stays the same. What we can do is we can bring out the exponent and then leave it to that. But the natural log of e is 1, so that becomes 1. So we'll find out that k is equal to the natural log of 5 divided by 3. So we can use a calculator for that. Natural log of 5 divided by 3. So we get 0.536. So now we know that our function can be more clearly defined as 100e to the 0.536 t. Now, what you didn't see was me going through and making a mistake and checking my answer. So that's why it's good to check your answer if it's not too difficult. So what I want to do is just plug 3 back in and make sure this works out. So I'll plug 3 in for t. So 100 times e to the 0.536 times 3 should be 500, which comes out to be 499.3, which is approximately 500. The reason is because I've just taken 3 digits for my k value. So that's close enough. Okay, so now what we can do is with the equation, we can now estimate the time in hours to double the population size. So what we're doing is taking this. Well, if we doubled the population, that would be 200. And what we're going to do is we keep k the same. We want to solve for t instead of k. Another way of thinking it, you could say double the population. You could just say it's 2. The population is doubled. If you took n of t divided by 100, that ratio would be 2, and you get the same result. Now, I can go from here to here just by dividing both sides by 100. So now, again, I can take the natural log of 2, and that's equal to the natural log of e to the 0.536 times t. So what happens on the right-hand side is when you take the natural log of e to something, it just becomes that exponent. That's because of the inverse, the fact that the natural log and the natural exponential are inverse functions of each other. Okay, so t is the natural log of 2 divided by 0.536. So plug that in our calculator. And so we get a time of 1.293 hours. And again, we can check that by evaluating the function again, 1.293. So that'll be 100 times e to the 0.536 times 1.293. So 100 times e to the 0.536 times 1.293, and I should get 200, which I get 199.98. So that does come out. So that check. So check here. Okay, so that's the first problem. The second one involves carbon dating. This is a exponential decay. So the quantity is going to be some initial quantity times e to the minus kt. So the first problem was exponential growth, and we had plus k. Here we have minus k. So in this, we're not given C0, I don't think, in this case. So we can also say that C over C0 is equal to e to the minus kt. So this is percent, or the ratio. So when t equals 0, you get 1. So let's just read it now. Carbon-14 dating assumes that the carbon dioxide on Earth today has the same radioactive content as it did centuries ago. If this is true, the amount of carbon-14 absorbed by a tree that grew several centuries ago should be the same as the amount of carbon-14 absorbed by a tree growing today. A piece of ancient charcoal contains only 15% as much radioactive carbon as a piece of modern charcoal. How long ago was the tree burned to make the ancient charcoal if the half-life of carbon-14 is 5,730 years? So half-life means, in our particular case, that the amount of carbon divided by the original carbon is 1/2. And we know that the time associated with that is 5,730 years. So we're going to again use that to solve for k. So you have 1/2 c over the amount over the original amount is e to the minus k times t, which is 5,730. So we can switch the numbers in the exponent, so we'll have negative 5,730 times k. Then we'll take the natural log of both sides. So what happens there is on the left-hand side we get the natural log of 1/2, and on the right-hand side we get negative 5,730 times k, or k is equal to negative, is that right? Yeah, k is equal to negative the natural log of 1/2 divided by 5,730. So I just divide both sides by negative 5,730. And if you do that, so we get negative the natural log of a half divided by 5,730. And my calculator says 1.21 times 10 to the minus 4. So that's our k value, so we can put it back in. C over C0 equals e to the minus 1.21 times 10 to the minus 4 t. So that's our equation. Now, in this problem, the second part of the problem says, how long ago was the tree burned if there's only 15% as much? So what we do is we convert 15% to the decimal equivalent, which is you divide by 100 and take away the percent sign. So 0.15 is the equivalent of 15%. And so we set the left-hand side. We're saying that 15% of the carbon that is available is based on the original amount is 15%. And what we do is now we go solve for t just like we did in the previous problem. So we take the natural log of both sides. So when you take the natural log of that, you get this. Here you have the natural log of e to the negative 1.21 times 10 to the minus 4 times t. But the e to the natural log of e to that is just the exponent, which is negative 1.21 times 10 to the minus 4 times t. And on the right-hand side, we get the natural log of 0.15. Okay, so t is the natural log of 0.15 divided by negative 1.21 times 10 to the minus 4. So I'm just dividing by this. That solves for t. And if you just think about it, if it takes 5,730 years to decrease to half, it'll take twice that amount to go to a fourth. And this is less than a fourth, so it should be more than 10,000. You know, if you double this, you're going to be about 11,000 years. So it's going to be greater than 11,000 years if we've done everything correctly. So natural log of 0.15 divided by negative 1.21 times 10 to the minus 4. And so the time is 15,700. I'm going to round it off years, which is more than 11,000. So that worked out okay. So I'll make sure I've answered all the questions. How long ago was the tree burned? Okay, so that's it. Okay, the next one. The management of a plastics factory has found that the maximum number of units a worker can produce in a day is 30. The learning curve for the number n of units produced per day after a new employee has worked t days is n equals 30 times 1 minus e to the kt. After 20 days on the job, a new employee produces 19 units. So what we need to do first is, like we've been doing, we have to find k, and then once we have k, we can answer maybe t. Now, k can be positive or negative here, because if you think about it, if k was positive and t was positive, you get e to a really big number, and that would be really big. So it's most likely k is going to be negative. And it's what I'm thinking about here is we want this number to go to 0 should go to 30. So if you become, t goes to infinity, this term we want to go to 0, and it does if you take t to the minus very big number. Remember, the exponential function looks like this. So this e to the kt, if k is negative and t is positive, you're going to be over here, and so the value of the function is going to approach 0. So that's another reason to think the k should be negative. Okay, so what we're going to do is we're going to say n of 20, which is 20 days, and that's equal to 19. So that's the number of units produced. 19. The maximum produced is 30 days. Is 30. Not 30 days, but 30 if you are super trained. You work there for years and years and years. So you'll get on the right-hand side 30 times 1 minus e to the k times t, and t is the number of days, and in this case it's 20 days. So that goes up there. So you can see the unknown is k again. So first thing you're going to do is you're going to divide both sides by 30. I'm going to switch k times 20 to 20 times k. Okay. Then you can subtract 1 from both sides. So you'll have 19 over 30 minus 1 is equal to negative e to the 20k. So then we can multiply by negative 1. So we'll get 1 minus 19 over 30 is equal to e to the 20k. So you always have to solve these things so you get e without any coefficient in front of it. And 1 minus 19/30ths is going to be 11/30ths. That's because 1 is 30/30ths, so 30 minus 19 is 11. Okay, so the next thing we're going to do is we're going to take the natural log of both sides. So what we end up with on the right-hand side is the natural log of e to the 20k. But natural log of e to something is just the exponent, so we get 20k. And then we can divide by both sides by 20. I'm going to put some parentheses around it here just to make sure we know that we're taking the natural log of this and that 20 is by itself. Okay, and as I said, we should expect k to be negative. So if it isn't, that won't be good, but I know it is. So, okay, so what we get is negative 0.0502. So the original equation now, n of t is 30 times 1 minus e to the negative 0.0502 times t. So that's the find the learning curve for this employee. First find the value of k. Then it says how many days should pass before this employee is producing 25 units per day. So again, we're solving for t given that we have everything here. So they're saying how many, what is the time to produce 25? So we put 25 on the left-hand side. So we'll divide both sides by 30. And then we'll subtract 1 from both sides. And we can multiply by negative 1, so we'll have 1 minus 25 over 30 is equal to positive e to the negative 0.0502t. So that's 5/30ths. So 30/30ths minus 25/30ths is 5/30ths. And 5/30ths is 1/6. So you can simplify that down. Okay. Then we'll take the natural log of both sides. So we get the natural log of 1/6 is equal to the natural log of e to the negative 0.0502t. So we get the natural log of 1/6 is equal to negative 0.0502t. So t is going to be negative, so we're going to divide both sides by 0.0502. So I get the negative when I divide, and then I divide that out. So now again, what should we expect as an answer? Well, go back to here. It took 20 days to make 19, so it's probably going to be, it's more than 20. So t is more than 20. I guess that's all we can really say at this point. So we have negative the natural log of 1/6 divided by 0.0502, and we get 35.7 days. Okay. Now the next problem is a logistic growth problem. So this is the logistic growth equation. They give us everything that we need to know. The carrying capacity is 1,000. If we let t equal 0, it would get e to the 0, which is 1. So we get 1 plus 9. 1,000 divided by 1 plus 9, or 10, is 100. So that's your initial amount. So that's the equation. See the figure. So it looks like this. Starts off 100. It increases quickly, but then it starts to slow down as the function, as the carrying capacity of the thing is reached, and the carrying capacity was 1,000. So you draw a horizontal line here at 1,000. This curve is ultimately going to go out that far. So what they're asking here to do is estimate the population after 5 months. And after how many months will the population be 500? You can almost guess it. So if you go here 500 and then you go down, it looks like about 13 or 14 months, but we'll get the exact value. So the first question was estimate the population after 5 months. So part A is just evaluating the function for 5 months, because they say t is measured in months. So we get 1,000 divided by 1 plus 9 e to the negative 0.1656 times 5. So let's see if you can do that in your calculator. So we'll put some intermediate values here so you can check it out. So e to the negative 0.1656 times 5 is 0.437. And so if we take 1,000, divide by, you have to make sure you put this in parentheses, 1 plus 9 times 0.437. And I come up with 202. And we can actually kind of check that on the graph. So if we go to the graph, here's 5 months, here's 200. It's just a little bit above 200. So that looks pretty good. The second one is how long was the question? The question was after how many months will the population be 500? So for that part, similar kind of deal. So B, what we're going to do is say 500 equals 1,000 divided by 1 plus 9 e to the negative 0.1656 times t. So we need to solve for t. Okay, so one thing you do is make these into two ratios, with this being divided by 1. And at that point, you can move the numerator in one side to the denominator in the other, or the denominator one side to the other. So what I'm going to do is I'm going to move this up to there and move that down to there. So I'll get 1 plus 9e to the negative 0.156t, 56t, is equal to 1,000 divided by 500. This one's divided by 1, but I don't need to really put that there. Okay, so that's going to be equal to 2,000 divided by 500. Next, I'm going to subtract 1 from both sides. So that will remove the 1 from the left-hand side. And if I subtract 1 here, I'll get 0. And if I subtract 1 here, I'll get 1. Then I divide both sides by 9. So I get 1/9. And then this is the time that I use the inverse relationship between natural logs and e. So that when I do that, I'll just get the exponent. Therefore, t is equal to the natural log of 1/9 divided by negative 0.1656. And the natural log of any number less than 1 is going to be negative, so I know that t is going to be positive. If it wasn't, I'd be not very happy. So I take the natural log of 1/9, I divide by negative 0.1656, and I get 13.3, I guess they're months. And again, we can check on the graph here. So it says if we go 500, here's 500, we go over horizontally to there, and then we go down. You can see, this is 12.5, so that's 13, so it's a little more than 13, and we got just a little more than 13. Okay, any other questions? Nope, that's it for that one. Okay, so those are all exponential models. We had exponential growth with bacteria. We had exponential decay with radioactive decay, carbon-14, but that would apply to things like uranium and any radioactive material. We have logistic growth, which is where you have usually in an environmental situation, ecology, where there's a certain limited number of organisms that can survive over the long run. Okay, the last bunch, not the last bunch, the next to last bunch are these pH values. And the reason you use this logarithmic model is because if you look at the hydrogen ion concentrations, the numbers can be all over the place. There's a large change in those for different pH value, different amounts of acidity. Whereas if you do a pH, they're usually between 1 and 12, maybe, something like that. So we're just going to go one, given one, figure out the other one. So here, find the pH given the hydrogen ion concentration. That's just a matter of plugging into the formula. So pH is minus log to the base 10 of 2.3 times 10 to the minus 5. So it's just a matter of knowing where log base 10 is on your calculator. So I can see mine easily, negative log. So if you have trouble doing that, you're going to have to talk to me and I'll figure it out on your calculator. So here I get a pH of 4.6. Now usually the smaller the hydrogen ion concentration, the less acidic it is. So I'm expecting the next number to be a higher number. Remember, low pH is acidic, high pH is basic. So we got pH is equal to minus log base 10 of 11.3 Well, yeah, it's not a whole lot. 11.3 versus times 10 to the minus 6 and 22.3 times 10 to the minus 5. This still is smaller, but not as big as it could be. Anyway, let's just do the calculation here. So negative log 11.3 e to the minus 6, and we get 4.9. So it is a little more basic, a little less acidic. Now, the next two, you just have to go the opposite way. So it says, compute the hydrogen ion concentration if the pH is 5.8. And again, we'd expect a higher pH means a lower hydrogen ion concentration. So what we're doing is solving for this hydrogen ion concentration. So to do this, we make the exponent on both sides, exponent with e being, well, actually, we need to have 10, not e, because it's log base 10. So we're going to have 10 to the 5.8 power is equal to 10 to the negative log base 10. Actually, well, yeah, let's go back one step here. We need to get the negative to the other side. So let's multiply by negative 1. Okay, now what we do is we'll say 10 to the negative 5.8 is equal to, so then we have 10 to the log base 10 of the hydrogen ion concentration. But these are inverse functions, so all we end up with is the hydrogen ion concentration. And it's not, so if you plug 10 and raise it to the negative 5.8 power, you'll get 1.6 times 10 to the minus 6. So that's your answer. It's not 5.8 times 10 to the minus something or other. You just have to plug that into your calculator and figure out what it is in scientific notation. And the final one of these, which is number 8, same deal. We've got a low pH, so we should have a high hydrogen ion concentration. So we get 3.2 is equal to negative log base 10 of hydrogen ion concentration. So we multiply both sides by negative 1. Then we raise 10 to the 2 powers here, to the 2 exponents that we have. And on the right-hand side, we get the hydrogen ion concentration, the unknown. And on the left-hand side, we take 10, raise it to the negative 3.2 power, which is 6.31 times 10 to the minus 4. So you can see I've got more hydrogen ions here because this exponent's small. Okay, the last problem's reasonably trivial. It's really, I think, included in the book because it just gives you another application of where logarithmic relationships exist. So let's just read it. So at 8:30 a.m. a coroner is called to the home of a person who died during the night. In order to estimate the time of death, the coroner took the person's temperature twice. At 9:30 a.m. the temperature was 85.7. At 11 a.m. the temperature was 82.8 Fahrenheit. From these two temperature measurements, the coroner was able to determine the time elapsed since the death. And the body temperature was related by the formula. So you end up with this formula. So this is the time, and this is the temperature. So all they're asking us to do is figure out, the elapsed time, and then we can subtract back to find the time of death. So really all we're doing is plugging it in. You could use either one of them. Let's see if how well the equation works. These two measurements were taken. These two measurements were taken 2 hours apart, so we should see the elapsed time is 2 hours apart. So let's try this. So t is equal to -10 times the natural log of t, which at 9 a.m. is 85.7 degrees minus 70, which is the ambient conditions, which means the temperature that the room is at. And then you've got the body temperature minus 70. Again, these are all degrees, so you'll end up dividing degrees by degrees, which will give you no units. That's one thing about when you have an equation that has logarithms and the equation involves things that have units. You always have to have the units have to cancel out, because you can't take the natural log of time or the natural log of degrees. So in this case, the degrees cancel out, so that's a good thing. Okay, so we have -10 times, it's the natural log, so ln of 85.7 minus 70 divided by 98.6 minus 70. And I get 5.997 hours. So based on that, since that was at 9 a.m., 9 minus 6 hours gives you 3 a.m. And if you did it with the second one, 82.8, the natural log of 82.8 minus 70 divided by 98.6 minus 70. So let's see what that is. So just changing 85.7 to 82.8, and there you get 8.04 hours. So again, if you take 11 now, because this measurement was taken 11, subtract 8.04 hours, you get basically 3 a.m. So you can see the equation is consistent. So that's it.